This is Dr. J. Mohan from Department of ECE. I'm in Institute of Aeronautical Engineering. My topic is signals and stochastic processing. Today I'm going to explain with elementary of signal. The elementary of signal is described as basic building block of construction of more complex signal. The signal stands as per unit step signal, unit ramp function, unit parabolic function, unit impulse function, sinusoidal function, real exponential function, complex exponential function, etc. First, we should go for the unit step function. Unit step function is defined as u of t. It is described as a mathematical form as u of t is equal to 1 for t is greater than or equal to 0. For t less than 0, it's represented as a 0. We represent for this one as a continuous time signals. For graphical representation, when t is started, for the t is started for 0, the amplitude is equal to 1. For all value of t, the amplitude value is equal to 1. This is a graphical representation of continuous time signal in unit step function. It's also possible to shifted unit step. It also possible to make for the shifted the function that is represented as u of t minus a. It's described as the mathematical form as u of t minus a equal to 1 when t greater than or equal to a, 0 for t less than or equal to a. So this is going to graphically represent as a when the t is present as a 0, when the t is present as a, then the signal is represented as a unit. After that, all t value, the signal is represented as a unit together as a continuous value. At the same time, this is also described for discrete time function also. The discrete time unit step function u of n is defined as a mathematical model u of n is equal to 1 for n is greater than or equal to 0, 0 for n is less than or equal to 0. It may be represented by the graphical model as when 0 is present, the signal is unit. Then after all discrete value of 1, 2, 3 as a positive value, the signal is represented as a unit. For like this one, we may represent. Remaining the negative portion, all is represented as a 0. This is represented as a unit step function. The unit step function in the discrete time signal also possible to do for the shifted version. The shifted version of unit step function as a discrete time signal u of n minus k is described as in the mathematical model u of n minus k equal to 1 for n is greater than or equal to k, 0 for n is less than or equal to k. This is also described for as a graphical representation when up to k is 0. After k, when the k is received, the value of amplitude value equal to 1. After k plus 1, k plus 2, all the value of discrete interval is represented as 1. So remaining portion is represented as 0. So the negative side also is represented as 0. This is shifted version of discrete time unit step function u of n minus k. Then unit ramp function. The continuous time unit ramp function r of t is that function which state that t equal to 0. When the t is 0, the mathematically represent as r of t equal to t for t greater than or equal to 0, 0 for t less than or equal to 0. So we may represent for the mathematical and the simple model. Already we discussed about the u of t. The u of t, what is it? When t is greater than 0, then the signal is represented as a unit. This is represented as a unit and t is greater than or equal to 0. The remaining portion is represented as 0. That's why what we represent for the ramp signal, r of t is equal to t u of t. This it will be going to represent for the graphical model as like this form. And t equal to 0, here we mention t equal to 0, then the t equal to 0 is represented as 0. If 1, the t equal to 1, this is also amplitude also increasing 1. So then 2, the amplitude also 2. That's after that you may join for all signal. We get it for the discrete time signal. Remaining portion t less than 0, it's represented as 0, all 0. That's why we call this signal as a sloped signal. So the slope value is equal to 1. It's a unit ramp function. At the same time, we may represent for the relation between unit ramp function as a unit slope. So how to represent for the unit ramp function as a unit slope? When r of t is equal to integration of u of t dt is equal to dt integration of bt is equal to t. Now the t value greater than or equal to 0. The t value greater than or equal to 0, then it's represented as 0. This is going to satisfy for this condition. So now what is that? If you receive u of t, then make to integrate, then you are getting for the unit ramp function. If we need for the u of t, but we receive for the r of t, then we may do for the differentiation between differentiate with respect of t, r of t we get for u of t. This is a relation between the r of t as well as of u of t. Here, next case, delay unit ramp signal r of t minus a is given by r of t minus a is equal to t minus of a for t is greater than or equal to 0, 0 for t less than or equal to 0. This is also, we may write the mathematical model like this form. R of t minus a is equal to t minus f a u of t minus a. So what is it, what it will be represent for here? Well, this is going to represent for the interval of the signal. What is it? For t greater than of a, then this is represented as a unit t. T less than of a, t less than of a, it's represented as a 0. So then we get for the same similar waveform here together. So this is represented as an alternate representation of mathematical model of delay unit ramp signal. We may represent for the graphical as like this form. Up to t is equal to a, then the signal is represented as a 0 for all negative value as well as a positive value up to t equal to a 0. So after that it will be going to increasing t plus 1, t plus 1, t plus 2, like that one. That the amplitude is equal to 2. This amplitude is equal to t plus 1 is 1. After that you may join for all signal, we get for the slope. This kind of signal is represented as a delayed unit ramp signal. So we may represent for the discrete time signal also, as in this case of unit ramp signal. So the discrete unit time unit ramp sequence R of n is described as R of n is equal to n for n greater than or equal to 0, 0 for n less than 0. R of n is equal to n u of n. So this n u of n we should write for this limit only. We may write for the graphical representation as like the form. So when 0, the n equal to 0, then it's represented as 0. For all negative value, all it's represented as 0 because of n is less than or 0. Then 1, it's represented as 1. The interval, discrete interval 1 is 1. 2 is represented as 2. 3 is represented. After that, you may join for all the line 1, 2. This is we call for the discrete unit ramp sequence. Next, we go for the shifted version of discrete time unit ramp sequence. It's represented as R of n minus k is defined as R of n minus k is equal to n minus of k for n greater than or equal to k, 0 for n less than or equal to k. This it will be right alternate mathematical model like this form. R of n minus k is equal to n minus of k u of n minus k. This u of n minus k, we should inform to that this is an interval level. Then we write for the graphical representation like this form. So now I take for the k is equal to 2. The k equal to 2 as a, that k is represented as a positive integer. When k equal to 2, that is up to 2, k equal to 2 is represented as a 0, then all the negative value, as in this case of here, it state for the, it satisfied for this condition. All this state negative value is represented as 0. After that, it is going to have the positive. When we increase 1, 3, k plus 1 is represented as a 3, then it's represented as a 1. K plus 1, that is 2 plus 1, 2 plus 2 is represented as a 2. 2 plus 3 is represented as a 5, it's represented as a 3. Then you join to that, we get for the shifted version of discrete time unit ramp signal, we get it. Then R of n minus k, here I represent as a R of n minus of 2. The 2 is represented as a positive integer. Then unit parabolic function. Unit parabolic function, we represent for the continuous time signal as p of t. As a mathematical form, p of t is equal to t squared by 2 for t greater than or equal to 0, 0 for t less than or 0, or we may write like this form also. P of t is equal to t squared by 2 u of t. This u of t we represent for the interval for both t is greater than or equal to 0, t less than or 0. That condition is represented as a unit. Then we represent by the graphical representation as like this form. So when 0 it started, then its substitute for the 1 is represented as a 1 by 2. That is amplitude 0.5. This is 1. Then 2 is represented as a 1. Then after you join for all these points, we get it for the unit parabolic function. This unit parabolic function also is going to happen for the shifted version of unit parabolic sequence. P of t minus a is given by, as a mathematical model, p of t minus a is equal to t minus of a whole square divided by 2 for t greater than or equal to a, 0 for t less than or equal to a. So alternate way to write for the mathematical model as p of t minus a is equal to t minus f a whole square divided by 2 u of t minus f I. This u of t minus a is representation of the interval period. For t greater than or a, t less than or a, the value is equal to unit. The graphical representation of shifted version of unit parabolic signal is represented as up to a, the positive integer. The a, all the values are 0 for the axis. Then after, it's going to happen for the parabolic cases. In the parabolic shifted version of continuous time signal. Next, the ramp function is derivative of parabolic function, and step function is doubled derivative of parabolic function together. For here, see, if we have the ramp function, if you do for the first, if you need to the ramp function, you do for the first derivative of parabolic function, we get it for the ramp function. Then if we need for the unit step function, 2 times if we derivative for the parabolic signal, we got for the u of t. This is a relation between the parabolic as well as a ramp signal, as well as a parabolic as well as a unit function. Next case, discrete time unit parabolic function p of n, how may represent as a mathematical model. P of n is equal to n square divided by 2 for n is greater than or equal to 0, for n less than or 0, or else we may write it for the p of n is equal to n square by 2 u of n as an alternate version. This u of n is made to represent for the interval of the n. The graphical representation of this signal, when n equal to 0, that is represented as 0. That remaining negative portion, all negative portions are 0 as for n less than or 0. Then we may write for the n equal to 1. What is that? 0.5. Then this is next sequence, next like that, as a parabolic case of unit time parabolic sequence we are getting. Then at the same time, shifted version of discrete time unit parabolic sequence. P of n is defined as P of n minus k is equal to n minus of k whole square divided by 4 to for n greater than or equal to k, 0 for n less than or equal to k, or P of n minus k equal to n minus of k whole square divided by 2 u of n minus k. This u of n minus k is represented by the interval of both the signal of positive as well as of negative case. So this one it will be represented by the graphic. This one represents as a graphical model. When here I take for the k equal to 3 as a positive integer. When up to 3 all negative values, it will be represented as a 0. After that it's going to happen for the discrete parabolic sequence for n equal to 4. That means k, that is n minus of whole square divided by is represented as a 4k plus 3 plus 1 4, 3 plus 2 5, 3 plus 3 6, like that one we going to increasing for the parabolic of discrete interval. Unit impulse function, this one is very very important for communication student as well as of signal analysis application. The continuous time unit impulse function del of t, also called as Dirac delta function. This Dirac delta function is represented as a mathematical model as del of t is equal to 1 for t equal to 0, 0 for t are not equal to 0. Then the graphical representation of continuous time signal in unit step function, when the t equal to 0, the amplitude is equal to 1. The remaining portion all it's represented as 0. It's also possible to do for the delayed unit impulse function. Then del of t minus a is satisfied as del of t minus a equal to 1 for t equal to a, 0 for t not equal to a. When the t equal to a is a positive constant, then the del of the unit impulse function is equal to 1. For here, the a, where the position is present for the a in the t, then values represent as a 1, that is represents a del of t minus of a. Then the integral of unit impulse function is we get for the unit step function. I write for the mathematical model u of t is equal to integration of minus into plus into del of t dt, or we get for the we need for the dt, then dt del of t is equal to d by dt, differentiation of with respect to t in u of t, then we get for the u del of t. This is the way we are making to convert for the unit impulse function into del function, or unit del function into unit impulse function. This is a property of continuous time unit impulse function. First one, it is an even function of time t. Why? Because of when del of t is present for only the t equal to 0, or if we change for the sign value of t, then even though we get it for the del of t only. That's why I should write for the del of t is equal to del of minus t. Then if you do for the convolution of x of t and del of t, then with respect of dt we get for the x of 0 only, because of our del of t is going to active only the portion of t equal to 0 position. So that's why I should write for the integration of minus into plus into x of t del of t dt is equal to x of 0, or integration of shifted version. If you take for the any shifted version of integration of minus into plus into del of x of t del of t minus dt, then where the action is going to happen in the del, there only is possible to get for the output. That's why I should write for the x of t 0. So here only this is a shifted property in the impulse function. Next, if you multiply with any constant in the time domain, its average of mod of del of t. So what the multiplication is happen in the time domain a. So that average mod of a is del of t is a third property. Then fourth property, if you shifted version of any signal in the del of t, you are getting for the same amount of signal. See, I'm going to multiply with x of t, del of t minus t0, then we get it for the x of t0, that will be multiply with the shifted version, but both it will be have the same. The finally what I'm going to write, the output is represented here x of t0. Anything if you are going to multiply with the del of t, where the del of t is going to active, that portion only we get for the output. Now x of t del of t is equal to x of 0, or x of 0 del of t is equal to x of 0. Next, this is going to satisfy for the conversion theorem also. The x of t is equal to minus into plus into d of integration x of del of t minus of dt. This is represented as a convolution statement. This pi property is going to satisfy for the continuous time unit impulse function. Next is a discrete unit impulse function. We represent for the del of n. The del of n as a mathematical model is represented as del of n is equal to 1 for n equal to 0, 0 for n is not equal to 0. As a graphical representation, when the n equal to 0, the amplitude is equal to 1. So remaining all the portion for 1 as well as minus 1, 2, minus 2, all its represents is 0 only. Then the shifted unit impulse function we call for the del of n minus f k. The k is represented as a positive integer. We represent by the mathematical model as del of n minus k is equal to 1 for n equal to 1. 0 for n is not equal to k. This is how we represent when now I represent as n is a positive integer, then k also is represented as a positive integer. Now in this k is equal to 3, I should take for the k is equal to 3 as a positive integer. Now the shifted unit impulse function I should write for the del of n minus of 3. So this is the way. When the n equal to 3, where the n equal to 3, the impulse function is going to active. Remaining part all, it's represented as 0 in the discrete interval of a signal. Next case, it's how this is also going to satisfy for the some property of discrete unit impulse sequence. Then del of n we need in the sense we must subtract with u of n minus of u of n minus 1. This is a shifted version. For example, to take what this is u of n. This is represented as u of n 0, 1, 2, like that, and we have u of n. Then u of n minus of 1. I should write this is represented as u of, where the n is 1, it represents as 1. This is 0 for 0. So then this is 1, 2 for 1, 3 for 1. So you can minus with both. This is u of n minus of u of n minus 1. What you are going to? So this portion is going to delete it. So this portion is going to remove from here because of we are subtracting. Only these portions are there. What is that portion? This portion n equal to 0, then it's represented as 0. As per this, both the direction is represented as 1 minus 1, all it will be represented as 0. Only these portions are there. That's why this signal is represented as del of n. So del of u of n minus of u of n minus 1 we received for the del of n. So second property is represented as a shifted version property of del of n. So you can shift it for any positive integer, that portion only we get for the 1. So shifted version del of n minus k is equal to 1 when n equal to k. Where the n present, then the signal is represented. Remaining all portion n is not equal to k is represented as 0. This is also going to satisfy for the input convolution statement. As per the convention statement, x of n is equal to k equal to minus into plus infinitive x of k del of n minus of k. Then fourth property is represented as a shifted version of n0. How much going to shifted for n0? Then we get it for the same kind of signal in the x of n. So the summation of n equal to minus into plus into x of n del of n minus n0, then x of n0. So where the shift is happened, we get it for this portion. So next we go for the sinusoidal signal. A continuous time sinusoidal signal I represent for the x of t is equal to a sin omega t plus pi. A is represented as a amplitude, pi is represented as a angular frequency in radius. Omega is represented as a angular frequency in radius. Pi is represented as a phase angle in the radian. So the pi is represented as the angle between this 0 to changes in the frequency. Omega is represented as our complete one period. That is complete one period. T is equal to 2 pi by omega. So the amplitude we call for the maximum, or is a positive as well as a negative, both the direction. So T is represented as one complete cycle of signal, that is represented as t equal to 2 pi by omega. Then pi is represented as a phase angle in the radians that will be present for the zero initial state to our amplitude where they are going to end. So this is the way we represent as a sinusoidal signal in the graphical model. The discrete time signal sequence is also given by x of n equal to a sin omega n plus of pi. So A is represented as amplitude, omega is represented as frequency, pi is represented as phase. This it will be going to happen each and every n instant. Previously, this one is going to happen for each and every t instant as a continuous time signal. So discrete time signal, each and every n instant it's going to happen for the sinusoidal sequence. So the graphical representation of sinusoidal sequence, here I may represent for 0 is 0, then 1 it's represented as here 1, then 2 it's represented as 2, then like that will be going to increasing for the amplitude from the positive amplitude to negative amplitude of each and every discrete interval. The total duration of this one we call for the t is equal to 2 pi by omega. So this one, the total instant is going to happen. The total instant. This is represented as how many samples are present for each and every individual continuous sinusoidal signal cases. Next, real exponential signal. A continuous time real exponential signal we represent by the mathematical model as x of t equal to a e power alpha t. A is represented as a real constant. Alpha also represents as a real constant. If the signal is getting to vary, depends upon the alpha case only. If alpha equal to 0, then the signal x of t is of continuous amplitude of all time. If alpha is positive, then alpha is greater than 0, then the signal x of t is a growing exponential signal. If alpha is negative, then alpha is represented as less than 0, then the signal x of t is decaying exponentially signal. So this is I'm going to represent by the graphical model. First, we represent alpha equal to 0, then a e power alpha t, this value is equal to 0, that means e power alpha 0 t is equal to 1. So that's why we get for the a, that is represented as x of t. If x of t is equal to a, but both t is present for the minus less than infinity to plus minus infinity less than of t less than of infinity, all the direction we get it the some constant. So that's why I should write for the graphical representation of both t for positive of infinitive as well as of negative and infinitive as a constant signal. That's why I represent for here constant amplitude for all time signals. Next case, if we go for the alpha is greater than 0, only is represent for the positive. What will be happen? The signal is growing exponential signal. So the signal is going to have for the growing for exponential together. If alpha is less than 0, then signal is representing decaying exponential signal. So first is going to have the higher amplitude. After that, reducing. It's not go for the 0. It's going to reduce. Is approximately is have for the some 0.0001 together when the t is increasing plus infinity. For here, the minus infinity side is not touching the 0. It's going to have some value, but it will be going to growing for the positive side of infinity of t. So next one is and discrete time real exponential signal. We represent for the a of n is defined as a mathematical model. X of n is equal to a power n for all value of n. So when a is greater than 1, the signal growing exponential. When a less than or 0 less than a less than or 1 sequence decays the exponential signal. When a less than 0, sequence take alternative signals. For example, when a equal to greater than 1 for the first case, what will be happen? It's going to getting for the exponentially growing for the signal for each and every discrete interval. When a is present, 0 less than a less than or 1, it's decaying exponentially as a signal is reducing together for first one is a maximum, then after is getting to reduced. Then last case, when the signal a is less than 0, the signal is taking alternate sinusoidal signal or alternate sine signals. So the negative side also have for the negative in the amplitude and the positive also in the amplitude is alternatively going to vary for the signal. This is represents a decaying real exponential signal a power n. Then if how for the x of n a power n is minus 1 less than of a less than of 0, then we get it for the signal as a positive. Negative side is going to have the maximum in the amplitude. After that, it's decaying alternatively. This is the way we represent for the exponential signal. Next one is complex exponential signal. The complex exponential signal we represent for the x of t is equal to a e power st. So a is the amplitude and s is complex variable. S is represented as a S is equal to sigma plus j omega. Then I should write for the mathematical model x of t is equal to a e power st is equal to a e power sigma plus j omega t is equal to a e power sigma t and e power j j omega n. A sigma t, this value I should use to cos omega t plus j sin omega t. Like that one I should write. Now the value of sigma and omega, we get different kind of waveform if it change. For example, I should substitute s equal to 0, I get for the constant amplitude. Next, I should substitute for the s equal to minus sigma, I getting for the exponentially decaying signal. I should give for the sigma equal to positive, then I get for the signal is exponentially growing signals. So this is the way we may represent as a signal in the case of discrete value. Then discrete complex exponential signal. Then discrete complex exponential signal we represent as a x of n equal to a power n j omega 0 n plus theta. This a power n I should take for the constant. This omega e power j omega 0 n plus pi I should write for the cos of omega 0 n plus pi plus j a power n sin omega 0 n plus pi. So this is I should write A always I take for the real numbers, and imaginary part of all complex exponential signal are sinusoidal signal. When A equal greater than 1, the amplitude of the sinusoidal sequence is exponentially growing, and magnitude of A less than of 1, amplitude of sinusoidal sequence exponentially decaying. Then we should write for the graphical representation of when A equal to greater than 1. Mod of A equal to greater than 1, what will be happen? The exponentially the sinusoidal signal amplitudes are getting to grow. Then A less than 1, that time what will be happen? The amplitude of exponential signal decaying together for in the stage of infinitive. Then rectangular pulse function we represent as a unit rectangular function is represented as a pi of t by tau. As a mathematical function, pi of t by tau is equal to 1 for mod of t less than of tau by 2, 0 otherwise. The graphical representation of rectangular pulse function is present only the mod of t less than of t by 2. That means minus t by 2 2 plus t by 2. It will be have the rectangular case. Next case is a triangular pulse function. The triangular pulse function is represented as a del of t by tau. Del of t by tau is equal to 1 minus of 2 mod of t divided by tau for mod of t less than of t by tau. 0 for mod of t greater than of t by tau. So this is going to represent by the graphical model as up to minus t by 2 plus t by 2. Here I mentioned for the mod of t less than of t by 2 plus t by 2. The value is represented as a 0 for both. Then as for the statement, then 0 is amplitude is equal to 1. Then join together for all interval, we get it for the triangular pulse function. Next, we go for the sine function. The sine function we represent as a sine of t is equal to 1 for t greater than 0, minus 1 for t less than 0. The graphical representation of sine function when t equal to greater than 0, all the values are positive, and t less than of 0, all the values are negative. So both alternative together for positive as well as negative. Sine function. The sine function is represented by the sine c t as a mathematical model. Sine t is equal to sine of t divided by 2 for minus into less than a t less than a infinitive. As a graphical representation, it's going to have for the Gaussian bell curve with the negative portion. It's all continuously decreasing together up to when t equal to infinitive. As well as the left side also when t equal to negative infinitive. This is represented as a sine function. Next is a Gaussian function. This Gaussian function we call for the g suffix e of t is equal to e power minus at t square for t is present by the minus into plus infinitive. Then this one is going to represent by the graphical model as a bell curve. So when 0 of t it's represented as a 1, remaining portion we get it for the like a bell curve is going to decreasing. The up to minus of 1.5 plus 5. After that it's go for negative. It's go for the 0 at negative stages. Both 0 as well as a negative stage in the Gaussian function. Up to this much, I'm going to stop this lecture in the signaling condition. Signaling condition, the basic signals.
Like, share and subscribe. Hit the bell icon for more updates.